Hi, and welcome to another Math 4 Honors lesson. I'm Kirk Weiler, and today we're going to be looking at Unit number 5, Lesson number 7 on graphs, limits, and asymptotes of exponential and log functions. This is kind of a tough topic to bite off in one chunk, and we're going to be doing a lot of different things in the lesson today. Primarily, we want to feel very comfortable with 3 graphs, and that's where we're going to begin. So let's take a look at the first exercise. Oh, I don't want my head right here. Okay, I'm going to move out of the way. All right, let's take a look at exercise number 1. In exercise 1, we're asked to sketch the graphs of y equals e to the x, y equals e to the negative x, and y equals ln of x without the use of our calculator. Now, I'd like you to pause the video right now and make an attempt at doing this. If, while you are working on this, you find that you can't figure out what the graphs of those 3 are without any other help, then what I'd like you to do is go to your graphing calculator, put them into, y1, y2, etc., and see what you get. But try your best, if you have to do that, to then look at the graphs and understand their behavior algebraically instead of just the pretty picture that's on the screen. All right, pause the video now. Okay, let's go through the graphs. All right, let's just make sure we've got the pen activated. Excellent. Now, let's first take a look at the graph of y equals e to the x. The key in understanding its graph is really understanding the graphs of all exponential functions b to the x, where b is greater than 1, right? Since e is a number that's just a little bit south of 3, right, 2.7, etc., then it falls into what we call an increasing exponential function, right? So it's going to look something like this. Right? It's going to look like 2 to the x, 5 to the x, etc. It's going to obviously have a y-intercept of 1. Now, you can think about y equals e to the negative x in lots of different ways. One way to think about it is if you've studied reflections across the y-axis, we know that anytime we negate the input, it's going to reflect the graph across the y-axis. That's one way to think about it. What graph? The graph that we just drew. Or, and this is a neat way to think about it, you can also think about it as 1 divided by e to the x. Now watch out, watch what I do here. I'm going to pull a fast one, which is the same as 1 divided by e, all raised to the x. And now the base falls into that category of being between 0 and 1, right? All exponential functions are characterized versus growth or decline based on whether their base is greater than 1, as in this case, or between 0 and 1. In the case where it's between 0 and 1, I got to scooch my graph in right here. All right, we're going to have a decreasing exponential, something that looks like this. Again, a y-intercept of 1 easily proven by putting in x equals 0 into this function. Now, the logarithm sticks out because e to the x and e to the negative x are both exponential functions. But the logarithm is a logarithm function. And remember, the key to understanding this thing is it is the inverse of y equals e to the x. And remember how inverses work? Everything switches on them. Inputs become outputs, outputs become inputs, x-intercepts become y-intercepts, y-intercepts become x-intercepts, etc. So I could actually create a table of values if I really needed to for this logarithm function. One value that I know on there immediately, because I know the point 0, 1 lies on the graph of y equals e to the x, then I know that the point 1, 0 must lie on the graph of ln of x. Let me write that down. Sorry, y equals ln of x. Right, so I know that this point must be on here. Here's the key, though. This function, y equals e to the x, has a horizontal asymptote of y equals 0. By extension, that means ln of x will have a vertical asymptote of x equals 0. Let me throw one more thing in there. I'm going to just change my color really quickly to red. As we've learned in previous courses, we also know that inverses are symmetric about the line y equals x. So if I took this graph, the graph of my y equals e to the x, poorly circled, and I reflect it across the line y equals x, I get a graph that looks like this. I'm going to go back to blue. Thank you. So I get a graph of the logarithm function that looks like that. Y equals ln of x. Okay, so that's exercise number 1. Now, this is the setup exercise really for the rest of the lesson, because as I think about limits and other things involving primarily e to the x and e to the negative x, not as much with the natural logarithm function, But I want to be able to visualize these graphs. I really want to understand the limits that show up in exercise 2. So take a look at exercise 2. In exercise 2, we're given 6 different limit questions. Remember, the limit is where the output or the y value of the expression is headed as the input heads towards a particular value. And here, we're very interested in x heading towards infinity, negative infinity, and in the case of the natural log, towards 0 from the right. So what I'd like you to do is I'd like you to pause the video right now, especially if you've had exposure to limits. If you haven't, this is going to be a little bit tough, obviously. But I'd like you to pause the video now and think about these limits in the context of the graphs that you have above. Okay? All right, let's go through these limits. Now, in each one of them, we want to appeal to the graph. So let's take a look at the limit of e to the x as x goes to infinity. All right, well, that solidly puts us on the first graph that we drew. And of course, what we see is that as x gets larger, as x heads towards infinity, no great surprise, e to the x also heads towards infinity. I would very much encourage you not to necessarily even look at the graph. I would encourage you to say, hey, look, e is about 3. So if I put in larger and larger exponents of 3, 3 to the 10th, 3 to the 100th, 3 to the 1 millionth, that gets enormously large, right? 3 times 3 times 3 times 3 again and again gets larger. On the other hand, look at letter B. Now we have the limit of e to the x as x goes to, and this is important, negative infinity. In this case, we can go back to that first graph again, but here we're traveling to the left along the x-axis, and the y-coordinate is simply getting smaller and smaller. So e to the x is headed towards 0. It's not headed towards negative infinity. Again, play around with some numbers. Think about like 3 to the negative 10th, right? That would be 1 over 3 to the 10th, and that is small. And that's only when x is negative 10, right? We're talking about heading to negative infinity here. That's a very important limit, by the way. Make sure you really kind of internalize that one. All right, let's go to the next graph, right? Now we want to take a look at e to the negative x. That may even be more important than e to the x in terms of limits. And you'll understand that eventually either in this course or other courses where you do a lot of modeling. So let's take a look at letter C. Letter C says, what's the limit of e to the negative x as x goes to positive infinity? Again, if we're sitting on this graph, what we see is that as x gets very large, e to the negative x is getting smaller, so that limit is headed towards 0. Again, encourage you to consider it. We could actually just use the exact same example, right? If I let x go to 10, then I have 3 to the negative 10th. Let x go to 100. It's still nowhere even near negative infinity. I would get 1 divided by 3 to the 100th, and this is even smaller than before. I mean, this is minute. Your calculator would probably tell you 0. All right, let's take a look at letter D. We're all the way down at the bottom. E to the negative x as x goes to negative infinity, we're going to be just headed in the opposite direction. Right now we're going to go to positive infinity. Up, up, up we go. And now let's take a look at the only 2 limits that in my mind are really all that important on the ln function. Let me explain why. The natural log function is nice and continuous, right? But it's got an issue for any values of x that are negative or x equals 0, in fact, right? The domain, maybe go back to that logarithm function. The domain of the logarithm function is x is greater than 0, right? That's my domain. There are no values of x that I can put in that are smaller than 0. Or even 0. So I can't ask what the limit of ln of x is as x goes to 0. I mean, I can, but it wouldn't exist. My question is, what's happening to ln of x as we approach 0 from the right? Well, what's happening is the y values are getting more and more negative, and in fact, they're headed to negative infinity. So make sure to know that limit. Likewise, when ln of x goes to infinity, where does ln of x go? This could actually be very, very visually deceptive. You might say, well, as x heads towards infinity, it appears like the ln might be heading towards a horizontal asymptote, but in fact it's not. The natural logarithm always grows. It grows very, very slowly. It makes the square root look fast. That's how slow the natural log grows. But it does grow. So keep that in mind. All right, I think I'm going to scrub out the screen. So take a look at the writing, pause the video for a moment if you need to, and then I'm going to erase the text, okay? All right, let's go on to the next problem. Okay, exercise number 3 and exercise number 4 directly relate to the limits and to the graphs that we just produced. So in exercise number 3, I give you 3 limit questions that involve exponential functions. All right? All 3 of these are very different in nature and challenging in different ways. So what I'd like you to do is pause the video right now and play around with these 3 limits. See if you can find them algebraically. If you can't, you might want to think about even putting them into your calculator to explore. But either way, take as much time as you need, and then let's come back and see how they're done. All right, let's go through the limits. Letter A and letter C, in my mind, are both very standard limits. So as weird as this is going to be, I'm going to go through those 2 first. All right, let's take a look at exercise letter A. In exercise A, we ask, what is the limit of 2 plus e to the negative x divided by 3 as x goes to infinity? One thing I always encourage my students to do when they're looking at a limit is make sure to understand what is changing and what is constant. There is no question that the 2 is a constant and the 3 is a constant. They are not changing. So the real question is, what's happening to e to the negative x as x heads towards infinity? Well, if we look at that graph of e to the negative x, I'm just going to do a very small sketch of it here. What's happening is, as x goes to infinity, e to the negative x goes to 0. Now, a lot of students actually want to say, well, then this limit is equal to 0. But it's not, right? The numerator gets closer and closer to 2 plus 0. The denominator stays at 3, and so the overall limit is 2/3. Got it? Remember, keep in mind what's changing and what's staying the same. Let's take a look at letter C, then we'll go back to letter B. Letter C is actually quite easy. In fact, if anything, it's sort of a trick problem to try to get you to think harder than you have to. Remember, one of the fundamental things about limits is that the first thing I should consider is whether or not I can do the limit by substitution. And that boils down to whether or not the function is continuous there. So in letter C, it's still good to understand that the 5 and the 3, well, they're not changing at all. Neither is the 2 here, but it's attached to that e to the negative x. So e to the 2x, well, that's changing, and e to the negative x, that's changing. And the question is, where are they going as x heads towards 0? Well, e to the 2x is headed towards e to the 0. Right? E to the negative x is headed towards e to the negative 0, but that's 0. Now watch out here, folks. Right? Watch out, little exclamation point there. I've had students before that do 2 times e and then they raise to the 0. Exponents before multiplication, right? Always remember your order of operations, really critical. So the numerator is 1 plus 5, the denominator is 3 minus 2 times 1, and that's going to be 6 divided by 1 for a limit of 6. All right, let's do the tricky one, letter B. This one's particularly tricky because students have a hard time dealing with infinity. I think that's kind of understandable. It's a pretty high-level topic. But this is what a lot of students will do. They'll say, well, 2 to the x, that's headed towards infinity as x heads towards infinity. And 3 to the x, well, that's headed towards infinity as x heads towards infinity. Then maybe many students will erroneously conclude that this is equal to 1. Let me just be very clear. It's not. All right? It would be very understandable, though. The reason it's not equal to 1 is that infinity divided by infinity is what's known as indeterminate form in calculus. See, infinity comes in different sizes, so it's really hard to say what infinity divided by infinity is. Watch out. In this case, infinity divided by infinity is going to end up going to 0. Why do I know this? Well, let me review a little exponent property with you. Right? You've seen this one before. If I've got a fraction raised to an exponent, I'll put it in terms of n, then I can raise the numerator to that exponent and the denominator to that exponent. That's just because of the definition of how we multiply fractions. But you see, we can use this property backwards. In other words, I can rewrite this limit as the limit as x goes to infinity of 2 divided by 3 raised to the x, right? Think about this. I really want you to consider this for a moment. Just a little mindful manipulation. But now here's the beautiful thing. Now we just have b to the x, where b falls in that 0 to 1 category. And we know those decrease, right? So this limit must be equal to 0. Okay? I hope you got that. Pause the video for a minute if you need to take a look at the text, because I think I'm going to scrub it out before I go on to exercise number 4. So pause the video if you need to. All right, it's gone. Let's take a look at number 4 now. In number 4, and really we have kind of a grab bag of problems at this point, so I apologize. All the problems now are kind of, if you will, non sequiturs. We skip from thing to thing to thing. Problem number 4, though, take a look. It says, Where will the function y equals ln of quantity x minus 5 have a vertical asymptote? And then it asks us to explain. I think that most of my students can get this problem, so I'd like you to pause the video right now, take a few minutes, and see if you can answer it. Okay, hopefully you figured out that ln of quantity x minus 5 has a vertical asymptote at x equals 5. And let's take a look why. One thing you should immediately know is that y equals ln of x minus 5 is a shift 5 right of y equals ln. And let me put that x in parentheses, even though it doesn't need to be there. So right, and then I think to myself, well, what does ln of x look like? I'm going to put the graph over here, which is a little confusing because it's right by the ln of x minus 5, but I'll make sure to clarify, right? So a very exaggerated logarithm graph, but it'll do the job, right? So we have y equals ln of x, and of course it's got a vertical asymptote of x equals 0, right? We saw that in the first exercise. But now I'm going to shift it right 5 units, right? And what that's going to do is it's going to give me a graph that looks something like this. Now, my students, I always say, try to incorporate the shifts in terms of just shifting the axes. So I now have this as the graph of ln of x minus 5. All right? Clearly, having a vertical asymptote, always want to write down the final answer of x equals 5. All right. Again, pause the video now if you need to take a look at the text, because I'm going to scrub it in a second. All right, let's move on. Next problem. Okay, so, whoops, we have a repeat. I don't know how that got in there. I pasted it 2 places. I think we'll just skip doing exercise 4 twice in a row, if that's okay with you, and I'm going to keep it in the video so I don't have to redo the whole thing. Let's take a look at exercise number 5. Again, grab bag of a problem. Exercise 5 asks us to determine all the solutions to a rather ugly looking equation, x squared e to the x minus 4x e to the x. What I'd like you to do is pause the video for a moment and try to solve this equation. All right, I'm going to let you pause the video now. All right, if you still weren't able to solve it because it just looks absolutely horrible, let me give you a little hint. Remember, there are 3 primary equation solving techniques. The first one is by just using inverses. But that only works if x shows up once, and x shows up 1, 2, 3, 4 times in this problem, according to my eyes. So that's not going to work. The second equation technique that I want you to be biased towards is the zero product law. In other words, if I can factor an equation set equal to 0, I can then set each one of the factors equal to 0. That's what we're going to use in this problem. The third primary technique is this graphical solution, but I want to try to avoid that if I can. All right, so I'm going to use the zero product law, ZPL. You know that abbreviation, right? Anyway, so I'm going to look at this binomial, and I'm going to see what I can factor out of it. Okay. What's obvious to me is they both have an e to the x in them, and they both have an x to the first. So I'm going to factor out an x e to the x, and what do I have left? I have an x minus 4, right? Now the beautiful thing is the zero product law is just set now. I have the product of 1, 2, 3 things, right? So either x is equal to 0, that's my first one, or e to the x is equal to 0, or x minus 4 is equal to 0, right? This one's easy, it's done, x equals 0. This one we'll come back to in a moment, and this one's pretty easy to solve, x equals 4. So right now we have 2 solutions at least, 0 and 4, and now the question is, well, what makes e to the x equal to 0? If you haven't gotten this far, ponder it a little bit, pause the video. All right, hopefully what you've come to the conclusion of is that it has no solutions, right? And I really want you to internalize this, okay? I really want you to think about what a solution would have to look like. For a solution to exist, e raised to that number would be 0. But if I have e to the 5th, well, that's e times e times e times e times e, I think. Hopefully I didn't just say e too many times, but whatever. E to the 0 is 1. E to a negative number, like let's say e to the negative 2, so I can keep track of it, well, that would just be 1 divided by e squared. That's not 0 either. So this has no solutions. And in fact, that's what we mean when we say that e to the x has a horizontal asymptote of y equals 0. It's going to approach y equals 0, but it's not going to end up touching it. All right. I'm going to scrub out the text one more time, so pause the video if you need to now to look at that problem. All right. Let's move on to the next page. Now we have the final problem. I don't know what happened before. Exercise number 6. We have a neat looking function. 8e to the x minus 9 divided by 4e to the x plus 3. The first part of the problem is completely exploratory. It says, using my calculator, I want to sketch the function using that window given. So pause the video now and use your Texas Instruments or Casio or Hewlett-Packard or any other brand that I've forgotten now, please don't sue me, and sketch that function. I think you'll see something that's really rather cool. All right, let's take a look. I don't have a grapher yet on this calculator that I can really show you, but I'm going to sketch the graph by hand. All right, and it's really neat for a variety of reasons. If you take a look at it, it ends up looking something like this. I think that's right. Does it have a positive y-intercept? I think it does. Anyway, what's kind of cool about this function is that it appears like it has two horizontal asymptotes. That's the answer to letter B. And it does. If you used a trace command, let's say on your calculator, something like trace, what you would find is that these y values are quickly approaching y equals 2, and down here, these y values are approaching y equals negative 3. And you'd see that easily if you traced along the curve. So try that. If you need to, pause the video now. All right, but what we want to now do is we want to explore algebraically why this thing's got two horizontal asymptotes. Normally when you have a rational function, remember these guys, like 2x squared minus 3x plus 1, let's say, divided by 4x squared plus 3. If I asked you what the horizontal asymptotes of those were, you would explore it as x went to infinity and as x went to negative infinity. I don't know why I wasn't getting the pen to write there. And what we would find is that either way, y was heading to 1/2. Think about why that is for a little bit. But what's cool is that it's the same either way, whether you head towards positive infinity or negative infinity. You get the same horizontal asymptote. On the other hand, in this case, you get different ones. So let's explore this. If you think you can do it on your own, if you think you can figure out why it's equal to 2 and negative 3, pause the video now and try to do the limits on your own. Okay, let's take a look at why it works. Strangely enough, in my own mind, this is the much easier limit to understand. So let's take a look at that. Let's look at the limit as x goes to negative infinity of 8e to the x minus 9 divided by 4e to the x plus 3. Here's why I consider this to be the easier limit. Again, think about what's changing and what's staying the same. The negative 9 is staying the same, the 3 is staying the same, so are the 8 and the 4, but because they're attached to the e to the x, they're gonna get involved in this calculation right away. And remember, what we want to know is that e to the x heads towards 0 as x heads towards negative infinity. But that means this entire term goes to 0 here, this entire term goes to 0 here, and the limit becomes 0 divided by 9 divided by 0 plus 3, that's negative 9 divided by 3, and that's negative 3. So that's why we end up with that horizontal asymptote. Now let's do what I think is the harder one to think about. Let's look at the limit of 8e to the x minus 9 divided by 4e to the x plus 3 as x goes to positive infinity. See, here it's a little bit harder. Here it's a little bit harder. So I actually want to go back just for a moment and talk about why this is quite easy to get that, right? And the reason why is that we always look at the long-run behavior, right? The long-run behavior. And the long-run behavior of a polynomial is dictated by its highest term, right? So we get 2x squared divided by 4x squared. The x squareds cancel, and we get long-run behavior of y equals 1/2, all right? But that's because x squared gets very large regardless of whether x goes to positive infinity or negative infinity. Down here, that's different, you see. As x goes to positive infinity, the negative 9 and the 3 are irrelevant, just like all this other stuff is irrelevant up in this problem when x goes to either infinity or negative infinity. So as x goes to infinity, and negative infinity, I'm going to switch back to blue, what happens is that the only thing that matters in the numerator is that exponential, because it's getting so large, folks. That's why, not because it's an exponential, but because it's an exponential that's getting very, very huge. So subtracting 9, adding 3, no big deal. But now we have a situation that's very similar to the rational functions in that the e to the x cancels. We have 8 divided by 4, and we get y equals 2. Right? That's kind of tricky. This was actually a modified problem I took from the multiple section part of the AP exam from a few years ago. Anyhow, pause the video one more time if you need to take a look at the text. Otherwise, I'm going to scrub it. All right, let's go on and conclude the lesson. So I want to thank you for joining me today. I hope that you got something out of the graphs, limits, and asymptotes of exponential and log functions. As always, you can link to the worksheet and the homework from this particular lesson by clicking on the video's description right underneath the video. For now, thank you again for joining me. I'm Kirk Weiler. This has been Math 4 Honors. Until next time, keep thinking and keep solving problems.